Hello, people. Welcome to the next lecture on Introduction to Arrays. The agenda for today is we'll discuss about space complexity, introduction to arrays, reversing an array, rotating an array, and dynamic arrays. To start with, let's quickly go ahead with the space complexity. Space complexity, or in a program or algorithm, how do we find this? Any space other than input and output. Okay, so max auxiliary or extra space, you know that is utilized at any point of time during the execution of an algorithm is defined as space complexity. So let's say my algorithm, it's a black box for now. Okay, and this is represented by big O notation. My algorithm, which has some inputs and I'll get some output. Apart from this, any extra space my algorithm is using for its execution, any extra space is known as space complexity. Let's take an example. There is a function call. Let's take function call itself stores some space in a stack before this function is called, is 4 bytes, and all my inputs, okay, int x, int y, int I'm considering 4 bytes. All these, if you see, these are the intermediate things apart from input or output. So my space, if you see, each element into 4, so it's 16 bytes. And if you see the space complexity, it will be order of 1, because 16 bytes is a constant memory space I can anticipate and assign. So the space complexity is order of 1. Let's take another function where my input is n to this function, and internally, if you see, I am using array of 10. We'll talk about arrays. For now, let's consider this is an array of 10 elements. Okay, each int is 4 bytes, so 10 elements, it's 40 bytes. Similarly, x, it's 4 bytes, y is 4 bytes. Int array of n elements, so 4 bytes into n elements, this is 4n bytes. So total space, if you see, maximum space is allocated for this array. So my space complexity is order of 4n. If we omit the constants, it is order of n. So this is how you find the space complexity. So you have to ignore inputs and outputs. Only the extra space we have to consider for our algorithm for the space complexity. Okay, right. Now we'll jump into the next topic of the day, which is introduction to arrays. Right. So I have given one example in the above. Let's write down that int ARR of 10. So this is collection of similar objects or data types. Here my data type is int, right? Collection of similar data types which we will store, okay, in continuous memory locations. So not only collecting similar objects or similar data types, storing them in continuous memory locations. Let's try drawing an array representation, right? I'm collecting all objects, I'm storing in containers, and my first address location, let's consider it's 4000, and my next location would be, each int will have 4 bytes of memory. So my next register address would be 4000 plus 4, right? 4 bytes, so 4000 plus 4, 4004, and next would be 4008, and go on. All these are my address locations. address locations. Okay, now int ARR of 10. What is this ARR? ARR is reference of the array, which will always have initial memory address location, initial address location. You can point with the ARR, here the naming notation. Okay, let's say I want to access some random element. I cannot always say in terms of addresses, right? This is a randomly assigned value. I cannot always say go to the 4004 location and get the value, right? These are randomly addressed. So the terminology for arrays will use in terms of indexes, right? So I have 0th index, next index 1, 2, 3, 4, 5. So in array, the indexes actually start from 0. So here, even if the addresses are randomly assigned, we always know where the element is residing. Now, let me try accessing. How do I access one element from the index? And why always we have to give importance to 0th index? Okay, let's say if I have to access some element, let's say I want to access index 4th. I have to know its memory location. How do I find its memory location, right? Array of, okay, let's consider a of 4. So I am trying to access 4th index. So general formula is, okay, we always take 0th reference or 0th element index reference, ARR 0th index plus 4th element into array type. So my first location was 4000, right? Plus 4 into array type is int, which will take 4 bytes, right? So this is 4016. So 4016 is the address location. So it's easy to find your address when you know the 0th index. So that is the reference. You don't need to do all these calculations. Now let's talk about printing an array. When I have to talk about printing an array or accessing an element of an array, how do you print and how do you access an element from array, right? So if you see array, let's take an example. Okay, I'll take array of 5 elements, 5 contiguous memory locations. Randomly, let me try accessing. Okay, let's take 6 elements. So 2, 3, 6, 1, 8, 7. I have 6 elements. I have to print each of the value, right? If you see, I have to walk through each and every element. For that, I would need a loop to loop through 0th index to size minus 1, n minus 1 index and I plus plus. I can write simply any, n is the size, here it is 6. I can simply write print of array of I. So I am accessing ith element and I am printing it. So to print, you should need to iterate over each and every element in an array. So this is, if you see, I have to access each and every element. So my time complexity would be order of n. Right? Now accessing an element, I want to access the 3rd index. By above, you can see compiler automatically will know the memory location. You don't need to actually iterate through 1, 2, 3, right? Similarly, how we did above for ARR of 4, ARR of 3 also you can access it at the constant time. So you always know the address. So it's only the constant time, which is the biggest advantage of arrays. Your space complexity in accessing an element is order of 1, or your access time is constant. So this is about printing an array, accessing an element, how array is structured. Now let's talk about some more interesting concept, reversing the array. I have an array, I have to reverse it. Let's take an example of size 5 and error of 1 2 3 4 5. Okay, and reversing, right? This is my input and output I am expecting is 5 4 3 2 1. Agree? So simple observation, the sequence is reversed, right? Let's write down the observations, let's not jump into conclusions. So if you see, if I give indexes 0 1 2 3 4 5 and here also indexes will remain constant, my 0th index in input is now swapped with 4th index in the output, right? 4th index. And similarly my first index is swapped with 3rd, second is 2nd, right? Second is 2nd, third index is swapped with 1st, and my 4th index is again swapped with 0. So if I have to define this, right, how this swapping is happening, if I am considering ith index is getting swapped with which one? That would be, from observation, that would be, if you consider n into consideration, you have to know n, right? From where to where I have to iterate. So it would be n minus I minus 1. You can apply this and see, if your I is 0, your n minus I minus 1, which is 5 minus 0 minus 1 equal to 4. So ith index is always getting swapped with n minus I minus 1. This is one way of looking into it, right? So let's write down this approach. Approach 1, I index swapping with n minus I. See, another way to look into this, right? I can consider I as one of the variable and n minus I minus 1 is another variable. Or this is the end, this is the start. So I am seeing two pointers. One is starting, one is at the start, one is at the end. So I can call this approach as two pointer, right? Keeping at the corners of the array, I am trying to swap. So let's write down, let's take an example. Let's take a different example. 5 2 3 6 1 4 3. So always I point I at the start, j at the end, right? And these two will get swapped. So your j is your n minus I minus 1 or end. Now next iteration, I is increasing, j is decreasing, and these are getting swapped, and so on, right? And if the size of the array is odd, your middle element no need a swap. Okay, if it is even, already it is getting handled, right? So simply I am having a two pointer starting from the beginning, one pointer, and starting another pointer from the end. I is increasing, j is decreasing, and each and every element is getting swapped. How do you swap generally? If you have two variables a and b, you have to swap its values. If you directly write a equal to b and b equal to a, in first instruction a equal to b is assigned, but in second instruction your a value will be lost, so you shouldn't do this. Generally, how do you swap? You take a temporary variable, first store the a, and to the a assign b, and to the b assign temporary back. This is the way you swap using a third variable. We'll use the same concept. Now we'll start from the first and the end, and we do the swapping. Okay, let's write down the code for this, right? Void reverse, void because I don't need any return type, I'm just trying to swap. int AR of array, and int n is the size. Then start, right? I need my starting position and I need my ending position to do a reverse, right? So as we discussed, we need two pointers. One is from the start, so int I equal to start, int j equal to end, int j equal to end. And we discussed we are doing using third variable for swapping, so that would be int temp, right? So if you see, I need to iterate until I and j don't cross each other. So always my I should be less than or equal to j, right? So yeah, until I is less than or equal to j. So while I less than or equal to j. So simply temp equal to ARR of I, index element from ith index will store in temp first, and at ith position we'll give ARR of j, and to the jth position we'll put back the value from temp. That's it. I and j element positions are swapped. I can close all the braces. My code is done. Is it done? No. I'm not increasing I, I'm not decreasing j. Let's include those two as well. Increase I for every swap, decrease j after every swap. This method you can call from any external method. I'm just writing the method logic here. If you see the time complexity, we can observe how many iterations this reverse is taking. If the size is n, right, we are only doing till half of the size, so it is n by 2 iterations. So my time complexity will be order of n. Am I using any extra space to check the space complexity? I'm using I, I'm using j for the pointers which are constants, and temp is also constant. So I'm only using constant space, so my space complexity will be order of 1, right, which is 12 bytes of space, constant space, but we'll only consider order of big O notation, which is order of 1, right? Yeah, this is about reversing an array. So one question in the above, how do you reverse from particular index, start and end? You just pass the start and end index, that's it, right? We already have that in place. Now rotating an array, rotate array k times in clockwise direction. This is one more interesting question. You have to rotate your array k times in clockwise directions, or simply to say you have to rotate your array k positions in clockwise. Either you can say k times, okay, or you can say k positions. If you encounter any such question, it is k times or k positions. Example, let's take a simple array 1, 2, 3, 4, 5. So I have to rotate this 2 times, right? So after first rotation, so size of the array is 5 here. After first rotation clockwise, my 5 is expected to come to first position. So 5, 1, 2, 3, 4. And next rotation, my 4 is expected to come first. So it would be 4, 5, 1, 2, 3. So this is my output. Let's make try making some observations here. Okay, after two rotations my input is 1 2 3 4 5 and my output is 4 5 1 2 3. So last two elements have moved to the first position, right? This is our observation. Yeah, let's start with the brute force approach. Iterate from 1 to k. So you have asked for k rotations, right? You can start from 1 to k and do a single rotation every time. For every rotation, what you need to do, bring one element from the back and swap it with the 0 and move all the other elements apart from that to one side right. This would be your brute force approach. So you can use a temporary variable to store the last element first and move all other elements one step right. This is a brute force approach. So for k rotations, you have to do k times such operation. Okay, let's write down the code for I equal to 1, I less than or equal to k and I plus plus. Temp equal to ARR of n and one more for loop. This for loop is to move your elements from its index to right. So I'll start from the back only. J equal to n minus 1, j greater than or equal to 1 and j plus plus. We are swapping till 0th location with last. So we'll move first location to n minus 1 all towards the right. So we don't touch the 0th index, right? So how do you do this? ARR of j, which is last index, equal to ARR of j minus 1. The before index element, we are moving it to position. So all the elements will move right till j equal to 1. That's it. And ARR of 0, I'll save the temp which we have saved earlier. And we'll close all the loops. Let's find out the time complexity for this. The inner loop will iterate for n times and the nested outer loop will iterate for k times, right? So simply it is the number of iterations is kn. So my time complexity obviously it's kn, order of kn. And my space complexity, am I using extra space? No, it's only temporary variable, so it's order of 1. So this is a brute force approach where we are getting order of kn, right? This is to rotate an element. Do you see any observation? Can we optimize this? Let's write down inputs and output. My input is 1 2 3 4 5. Input and my output is 4 5 1 2 3. So if you see, first three elements in the input are moved to the last three positions. Apart from this, if we are saying clockwise, so clockwise last two elements are moved to first two positions in the output, right? Clockwise last two elements in the input are moved to first two positions in the output. This is our observation which will help us solving this. Let me reverse the entire input. Let me try reversing the entire input. So it's 4 5 3 2 1, right? Now if you observe, first three positions are came to last three. Internally they can be still arranged, but my last two positions came to first positions in the input. So one reverse operation has done half of our job, right? This is our observation. Now internally if I reverse 4 and 5 and 3 to 1, so I am reversing an array in some range, right? 4 and 5, this is 1 2 3. If you reverse internally, this is your output. So I have done 3 reverse operations on the input, right, which has resulted me the output. But what matters is the index from where to where I am reversing. So clockwise 4 and 5, two elements which is equal to the k value. So I have to reverse from 0 to n minus 1 first, then from index 0 to k minus 1, and from k to n minus 1. So how many elements you have to reverse, right? That you will know based on your k value. That's it. So 4 and 5, only 2 elements, 2 rotations I was asked to do. So from index 0 to k minus 1, that is 0 comma 1 has been rotated. Apart from that, k to n minus 1 is rotated again, which is 2 to n minus 1. So let's write down all this for our understanding very clearly. So reverse of 0 to n minus 1, that is my first operation, which will reverse the entire array. That is 5, 4, 3, 2, 1. Again reversing first 2, that means 0 to k minus 1 positions will give you an array of 4, 5, 3, 2, 1. Now again I have to reverse the next elements. That index is starting from k and ending at n minus 1. So 3 times reverse is enough to make it as, right? What matters is a k index from where to where. This is rotating your array k times. That's it. Reverse code we already discussed earlier. Do you see any problem here? I am trying to access k index, right, or k minus 1 index. What if my k is greater than n? What if my k is greater than n? Here I wrote time complexity, it's order of n, space complexity order of 1, because all of them are happening one after one. But what if k is greater than n? Will this work? So still we can optimization to handling the edge case. What if k is greater than n? Let's take one example. For time convenience, I will do 5 iterations of it clockwise. So after 5 iterations, if you see my k equal to n, the array is repeating itself, right? The array is repeating itself. So either k equal to n or k equal to kn times, array will always repeat itself. So if k is greater than n, what we can do is we can simply do a modulo operation, which will make sure that k lies between 0 to n minus 1. So let's take an example, k equal to 100 and n equal to 5. 100 rotations they asked, right? 5 modulo 100, sorry, it is 100 modulo 5, which is equal to 0, right? So you don't need to actually do any rotation, it's an array itself. So you have to introduce k modulo optimization for your earlier rotate code. So it's the same code where you reverse 3 times based on your k. Okay, what you need to add is, before passing this k, you have to add k equal to k modulo n. Let's write down the code quickly. It's all same. You have inputs of array and size and k. So k equal to k modulo 10. Then we can write all the three reverse operations. The reverse function we created earlier. Array of array n, and first we have to reverse entire array. So start and end is 0, n minus 1. Next reverse of array n from 0 to k minus 1. This is the exact attributes I am writing here for that reverse function. Next reverse of array n k index to n minus 1. Right. That's it. This is a code for rotate. And once you have modulo handling here, even your edge case is solved. Time complexity, simply it's order of n. Space complexity is order of n. That's it. Thank you folks. Thanks for the day. Okay, let's revise about arrays, advantage of arrays, and is there any disadvantage of array. Advantage of array, we have seen that it has constant access time. Disadvantage is the size of the array is fixed. Okay, and if we try accessing kth element, more than that size, it will go out of index, right? So my size of the array is always fixed. That is a disadvantage in array. What I am trying to look is, I need a constant access time plus I need some variable or dynamic size. How this can be achieved? For this we have the concept of dynamic arrays. So dynamic arrays means the size will automatically adjust if you try adding elements more than its size. One such example is array list in Java. So which will give you constant access time plus your size of the array is dynamic. So sometimes the time complexity will be constant, sometimes it depends on the size of the array. But for such we'll say the time complexity is amortized. Sometimes it's constant, sometimes it depends on the size of the array. Yeah, that's it folks. Thanks for listening to the video on introduction to arrays.